I think we can handle recursive types.
Yeah, it's not to check, but it's kind of cool that it just checks out.
Yeah, exactly. So I've been going through all the axioms.
Okay, thank you very much, Alex. I think we have to move to the next talk. And we can discuss offline. So Dominik, if you can share your slide now. In the meantime, there is a question about trouble getting the feed. I hope it's not related to the talk, but with technical questions. So there is a lunch for technical aspects if you need some help. Okay. So Dominik, can you share your slides?
Yes.
Okay, great. We can see your screen.
Okay, excellent. And can you hear me also?
Yes, we can.
Okay, great. Okay, hello. Yes, so I'm Dominik, and I'm going to talk about some aspects related to optimization and gradient descent and how this ties in with programming languages. So a very common task in Bayesian machine learning is to optimize expectations of functions. And I'm particularly interested in functions expressed in programming languages where you have conditionals, so the function is in general not continuous, let alone differentiable. And I'm also going to focus on settings where the probability distribution is independent on theta. And this is a scenario which arises very frequently in the maximization of the elbow for reparametrized models in variational inference. And there you can sort of factor out the dependence of the guides into some transformation. And the main benefit of the reparametrization is typically that the variance is reduced. So now, because, well, this is a very general class of problems, they are typically not convex, and the best thing we can hope for is to find stationary points, that is, points where the gradient vanishes. And one of the common techniques to tackle this problem is stochastic gradient descent, where in each step we follow a Monte Carlo estimate of the gradient. However, unfortunately, Li et al. Have shown at NeurIPS 2018 that the reparametrization gradient estimator is biased for non-differentiable models. A very simple example where we can see this effect is the following, where we have -1/2 times the parameter plus a Heaviside function centered around the latent plus the parameter. And there, if we sort of figure it out, then we see that the expectation of the gradient estimator is minus theta. But unfortunately, the true gradient looks slightly different. And therefore, in particular, vanishing gradient estimators does not imply stationarity of the original problem we are actually interested in. And in particular, even if stochastic gradient descent converges, it may converge to the wrong point. So the main contribution of our work is to present a modified version or variant of stochastic gradient descent, which provably converges to stationary points for a mildly restricted class of programs. And the approach we take is to smoothen the potentially discontinuous function using sigmoids with some accuracy coefficients, and then to optimize the expectation whilst simultaneously enhancing the accuracy in each step. And in this talk, I'm first going to introduce the programming language, which explicitly takes care of the reparametrization. And I'm also going to briefly give some intuition about what the type system does and how the smooth semantics works. And then I'm going to briefly discuss the diagonalization stochastic gradient descent procedure and its convergence property. Okay, so the programming language we take is basically a simply typed lambda calculus with reals, addition, and multiplication. So in particular, we can express polynomials, and we also have conditionals, so we can get some discontinuities. And we also have the slightly non-standard sampling construct, which immediately applies a diffeomorphic transformation. And in particular, we can sample from, for example, arbitrary normal distributions by sampling from the standard normal and then applying the usual affine transformation to it. And now, phrased slightly more technically, the problem we are interested in is the optimization of the expectation with respect to the multivariate standard normal of the value function of a term, where the value function is in the sense of Borgström. So essentially the deterministic function which yields for every parameter and every trace of samples the value we reduce to. And as pretty much an immediate consequence of the fact that we can, well, only express piecewise polynomials, we get that the expectation is always well defined. So now let's briefly discuss the type system, or the restriction we impose on the programming language. And this is a pretty mild restriction, and it only says that guards cannot directly depend on the parameters, but they may do so after transformations. So we can't branch on whether parameters are negative, for example, and we can't disguise this by using some lambda abstractions. But what we can do is we can check whether some transformed variables are negative or not. And the transformation, of course, depends on the parameters in general. And we can also do slightly more complicated things. And this is precisely the example we have seen in the beginning. And now, in order to link the type system with the value semantics, we use some reparametrisation-aware symbolic execution, which is a slight variant of what we used in our ESOP paper last year. And well, the main idea is that we collect the constraints due to branching, and we also replace these kind of combined sampling and reparametrization constructs with fresh sampling variables, and we keep track of the transformations we perform. And in slightly more detail, whenever we have a typable term of type real, then the operational or the symbolic execution evaluates to a polynomial term, and we keep track of sets of polynomials gathering the constraints due to branching, and we also keep track of the diffeomorphic polynomials due to the transformations. And then we can see that the standard value semantics essentially boils down to evaluating the polynomials or the polynomial term for the branch for which the parameters and latent satisfy the constraints of the branching polynomials. Or slightly more verbosely, this boils down to evaluating the product for every constraint in the polynomial or in the sets, and checking whether the polynomial applied to the transformation of the latent is negative or not. And of course, we have these indicator functions, and they are what causes the discontinuities. So what we do in our smooth semantics is not to use the indicator functions, but to apply sigmoids to them instead. And the sigmoid here depends on some accuracy coefficients, which we can improve. So we can make it essentially steeper and closer to the Heaviside function. And in that way, well, we can sort of make it arbitrarily precise intuitively. So the smooth semantics is not only of theoretical interest, but we can also actually compute it, essentially by just using a variant of backward mode automatic differentiation, which keeps track of the constraints due to branching. And now, as pretty much an immediate consequence of the fact that we are only dealing with smooth function, or that we have smoothed the function, we obtain that for every fixed accuracy coefficient, the estimator is unbiased. And therefore, we can essentially just apply stochastic gradient descent for each fixed accuracy. But of course, this does not necessarily tell us anything about how this solves the original problem we started off with. But we also know that the gradients converge uniformly to the actual gradients, which is very useful, because then whenever we fix a kind of error allowance, we can find an accuracy coefficient such that whenever we find stationary points in the smoothing, then the gradient of the actual problem we are interested in has only a norm of at most the error allowance. And the key trick how we can prove this is to reformulate partial derivatives with respect to the parameters in terms of the gradients with respect to latent variables. And then we can perform a integration by parts, essentially. And now, as a next step, if we are not content with, well, having this kind of, at most, this error allowance, we can also ensure that we actually converge to the to a stationary point original problem, so the unsmoothed problem, by increasing the accuracy in each step. So where in step K, we use the cave smoothing, essentially. And now, sort of, by tweaking the standard proof of the conversion of stochastic gradient descent a bit, and by taking into account sort of the properties we have already seen, like the unbiasedness and the uniform convergence, we can show that actually for every typable term of type real, a diagonalization stochastic gradient descent sequence is either unbounded or there's a stationary accumulation point, which is quite nice. Okay, so then finally, let's discuss a bit related works. So, I mean, in the beginning, I said that Li et al. Have, well, noted that the reparametrisation gradient estimator is biased, and they have also come up with a way to mitigate this. So they have modified the reparametrisation gradient estimator for non-differentiable models by adding an additional non-trivial boundary term. Unfortunately, this boundary term has to be computed, and they only discuss an efficient method to compute it for affine guards. Furthermore, they are also only concerned with the unbiasedness of the gradient estimator, but this is of course only a necessary requirement for the convergence of optimization procedures. So in particular, they don't talk about the convergence of stochastic gradient descent. And they also don't really link how their restrictions on the language relates to the programming language, or indeed recursion. So in this work, however, we have seen, well, how we can use a simple or a relatively simple type system enforcing a quite mild restriction on our programming language. And we have also seen a smoothed semantics, which avoids explicit computation of boundary terms. And we have seen how we can not only guarantee unbiasedness of a optimization procedure, but we have also shown convergence of the diagonalization stochastic gradient descent. Our result has a very asymptotic flavor in the sense that for each accuracy, our smoothing, well, is an approximation. So there is an error to it for every fixed approximation, but we can improve it systematically. As ongoing work, we are currently conducting an experimental evaluation, and we hope to get some solid results fairly soon. And in the future, of course, it would be nice to also incorporate recursion and to go beyond polynomials. And I would assume that this pretty much boils down to just making the type system a bit more complicated. Okay, so that's pretty much all I intended to say, and I would be happy about any questions.
Okay, thank you very much, Dominik, for your talk. If you have questions, please just ask them in the Q&A chat, or you can raise your hand so that you can go into the stage and ask your questions. So in between, when people are asking on the chat, I have some question. So could you tell us a little bit more on your evaluation? What kind of result you are looking for, on what kind of examples, or you said you are studying the performance of your result and doing some evaluation?
Yeah, exactly. So, well, we are currently comparing it to the results or to the benchmarks by Lee et al., which are kind of quite heavily based on branching behavior. But so far, we are still in the ongoing stage, so I can't really report on anything yet.
Okay.
But we hope that also, because they are focusing on affine guards, we also hope that we can sort of solve a bunch of problems which they can't deal with because it's not within their scope.
Okay, so I have another question. You said that you were replacing the 0,1 function, this one by a sigmoid at some point in your talk. So what is the effect of replacing it by the sigmoid? It's one of the slides before.
Well, I mean, it becomes smooth.
Yes.
And then the gradient, kind of, I mean, the problem with the standard reparametrization gradient is that it kind of only looks at the partition you are in. So, and it does not take into account at all whether there's a break. So if you have this sharp break, then this is never taken into account. But here, if you are kind of close to the where the jump happens, then by taking the sigmoid and differentiating through the sigmoid, then this is going to be taken into account. And that's what
do you have to parameterize it to be quite near the jump, or I mean, how do you control the approximation that you are doing by replacing the 0,1 function by a sigmoid?
Well, essentially, what one does is one just multiplies this with k. So sigma of k is just essentially k times the argument.
Okay.
In that way, sort of, it becomes ever sharper.
Okay, and so that you can have control on your approximation if you do that several times.
Yes.
Okay, great. So thank you very much. So I cannot see any more questions, but perhaps people will ask you privately afterwards. So we can clap again for Dominik, and I think it's the turn of Carol. So if you can come to the stage. Thanks again, Dominik.